Dr. Berkin, Massachusetts Genel Hastanesi ve Harvard Tıp Okulu'nda biyomedikal görüntüleme için Martinus Merkezi'nde radyolojide yardımcı doçent olarak görev yapmaktadır. MRA için veri toplama ve reconstruction teknikleri geliştiren BİLGİÇ Reconstruction Acquisition for Image and Neuroscience laboratuvarını yönetmektedir. Buyurun lütfen.
Davetiniz için teşekkür ederim. So I wasn't sure how to translate most of this stuff, so I'll be speaking English. I preemptively apologize for that. So my title is AI Technology Enables Faster and Higher Fidelity MRI. And here is a brief outline of what I want to show you today. I want to first give some background on MRI data acquisition and image reconstruction briefly, as well as giving an overview of my research in the lab. Then I'll talk about some applications which are facilitated by AI in terms of fast clinical imaging as well as efficient quantitative MRI. And I'll also mention some applications that are enabled by AI in terms of looking at safer MRI acquisitions via gadolinium dose reduction. So what I mean by facilitated versus enabled is that there are existing physics-based solutions to some of these acquisitions in terms of fast clinical imaging, but these can of course be much improved using AI technologies. But there are cases where we don't really have a physics-based solution, and in this case we can rely on AI to be able to enable such clinical applications. With that distinction, I want to begin by talking about some of the recent hardware innovations that we can rely on. For instance, we are now having access to 7 Tesla clinical scanners, as well as higher field strengths. So these give us more SNR as well as contrast, so we can push the limits of spatial resolutions in this case, as well as high performance gradients. We have this Connectome 2.0 scanners at the Martinus Center, as well as the next generation 70 magnet at the Berkeley. These have an order of magnitude stronger gradients, up to 500 millitesla per meter, compared to some of the clinical scanners, which are about 40 millitesla per meter. So almost an order of magnitude. So with these we can do better diffusion and image encoding, as well as having the ability to look at structural and functional connectivity of the brain in finer detail than previously possible. And finally, we have access to receive arrays that have 64 channels or even higher, and this gives us the ability to do additional spatial encoding and in some cases additional P0 main magnetic field control. So where does my research fit in? So we basically develop new acquisition and reconstruction technology to take better advantage of such new hardware. And the goal is to enable higher fidelity, resolution, as well as efficiency. And I think of this as high definition MRI. And in the bottom you can see some examples of this holistic approach. So I want to briefly talk about MR physics so that we are all on the same page. So we always have this main magnetic field when you enter the magnet that kind of points in the Z direction. This gives us some net magnetic magnetization, which we can image. And to be able to do this, we have to interact with these spins. And we do this by exciting them with just a copper coil at radio frequencies. And this allows us to excite these dipoles. And using another copper coil, we can receive these RF signals. But the problem here is that how do we differentiate signals that come from different locations, and how can we make an image out of this? So we need some sort of a spatial differentiation, and to be able to do this, we use these additional magnetic fields that come from these GX and GY gradients. There's also a GZ coil, but I am omitting that for the sake of simplicity. So if you turn on this GX gradient, what it does is to create an additional linear magnetic field. You can see that the spins on the left-hand side of the monitor now process a lot faster because they experience a higher magnetic field, whereas the guys on the right-hand side are now processing much slower. So this means that we've been able to encode some of the spatial location information into the precession frequency of these dipoles, which is exactly what we need to be able to get an image out of MRI. Of course, we can play this game on multiple dimensions if we turn on this additional GY gradient as well. And MR is basically a Fourier encoded imaging modality. How does this work? We basically turn on this GX gradient. This gives us one line of data point in this Fourier space. Then we turn on our GY gradient. This puts us at a slightly higher position. Turn on GX again, get one more line in our data matrix. If we do this so on and so forth, we obtain this entire data matrix, which we can then take an inverse Fourier transform and finally obtain our spatial image. So how do we do this Fourier encoding? We need certain constraints. So to be able to obtain this brain image, we need a certain field of view that covers the entire head. And that puts some constraints on how finely we have to sample in our Fourier space. So if this, in this case, if we skip every other line, what happens is that now the scan is 2 times faster. We call this R equals 2 acceleration, which is quite helpful. But the problem is that now the field of view is half the size, so we get these aliasing replicas that we have to somehow get rid of so that we can do accelerated imaging. And luckily we have access to these multi-channel coils. When we go into the scanner, this encapsulates our head, and each of these coils see a slightly different view of this object. And using this redundancy, we can begin to recover the aliasing-free true object out of this undersampled data. So that's how we do fast MRI. And now I want to switch gears and talk a little bit about clinical imaging. In this case, in the clinical domain, most of the acquisitions are done with 2-dimensional slice-by-slice acquisitions, and these can take up to 30 minutes, which is really not efficient. And if you want to accelerate, you only have one degree of freedom in this left-right dimension. And if you do just 5-fold acceleration, you can see that this image quickly becomes unusable because of artifacts. And what we have come up with this very crazy acquisition that gives us more than an order of magnitude acceleration and boosts the image quality. We do this by fully harnessing the degrees of freedom in these multi-channel coils so that we can provide high resolution with more speed and information. With this technology, we've been able to come up with a 6-minute multi-contrast exam at 1 millimeter resolution to provide a comprehensive neuroimaging protocol. And we also saw that this highly accelerated acquisition gives comparable diagnostic information relative to a standard scan that is at a much slower pace. This is now routine at mass general hospital brain protocols, and one of these acquisitions have now become a Siemens product as well. And with our colleagues at Boston Children's Hospital, we are looking at fast and comprehensive pediatric brain exams. You can see one such example in this figure. And with a collaboration with our colleagues at Sağlığın Medical, which is a startup, we are trying to make use of AI super resolution to further accelerate these acquisitions. In this case, we have a 1.5-fold additional AI speed up. When you combine this, we get this drastic 13.5-fold acceleration so that this whole brain acquisition can be completed in less than 30 seconds with this synergistic combination of AI and wave encoding. And the point here is we would like to obviate the need for sedation or anesthesia in these pediatric brain exams. So these were all standard MRI. In this case, everything is qualitative. We have system-dependent pixel synthesis. This is basically how we do imaging most of the time. But in the realm of quantitative MRI, the goal is to obtain objective and tissue-specific parameters. These are mostly known as T1 and T2 numbers. The point of this is these are very robust to hardware imperfections and they are more reproducible. From these, we can also simulate standard images, but the caveat is that these often take very long acquisition times to obtain. So we've been able to accelerate this quite a bit as well with this very colorless acquisition. Now we can provide these T1, T2 maps from a 3-minute acquisition at 1 millimeter resolution, and this is all physics-based. And the acquisition itself is very simple. We just get this pulse sequence with 5 different contrasts that has T1 and T2 sensitivity. And we can, of course, combine this synergistically with model-based deep learning. In this case, wave model is what we came up with. And in this case, we can go down to 2 minutes at 1 millimeter resolution at a 12-fold accelerated case. And in this simulated case, you can see T1, T2, and flavor-weighted data, which we can synthesize out of our parameter maps. But if you do this from a standard reconstruction, you can see that there's a drastic loss in data quality. So how does this work? We can incorporate MR physics in terms of the Fourier encoding as well as multi-channel arrays into our deep learning model. We can also do joint reconstruction across these 5 contrasts to export this nicely. But this was a supervised training paradigm in the sense that we scanned 10 different subjects at 2-fold accelerated acquisition, so these were relatively slow, from which we could obtain high quality reference images with which we can train our model. So what else we can do? We can actually do a decomposition of our Fourier space data across time to be able to resolve hundreds of images. We can do this by going back to our physics simulation if we know the T1 and T2 of every single combination of physically possible voxels. We can actually simulate and predict what the signal time course would look like. We can then go ahead and take a singular value decomposition of this to obtain a succinct representation, which we call basis functions. Then we can perhaps reconstruct these using what we call subspace reconstruction. Indeed, if we do this, we can resolve hundreds of images. We basically get an image per about 5 milliseconds apart. And of course, we can also do a conventional dictionary matching to be able to obtain the underlying parameter maps as well. So how do we do this? Without going into too much math, we have our decomposed data sampling masks or subspace bases, which we get from our MR physics simulations. From these, we would like to reconstruct these unknown subspace coefficients. Of course, we can do this with some optimization, where we can add additional regularization. In this case, we use a specific way of doing this, which we call zero-shot self-supervised learning, and I want to talk about this in some detail. This is what we call zero deep sub. Here, it's zero-shot and self-supervised in the sense that there is no need for an external training database. This works directly on subsampled Fourier data from each individual subject without having to acquire additional data. We start from our decomposed Fourier space, which is already undersampled. We can segregate this into 2 different parts, training, and we can further hold back some of the samples and use these as a validation case. On our training data, we can train this unrolled reconstruction network, and on the validation set, we can figure out when to stop training this model so that we don't overfit. So having done this, even at 10-fold acceleration, we can nicely observe that we can resolve more than 600 images. And we can also go back and check in time. We can basically simulate any time point that we would like to look at, basically freezing as well as obtaining time result information across many different time points. Of course, from this acquisition, we also get our parameter maps. In this case, a 2-minute acquisition from which we can synthesize clinical contrasts, such as these T1, T2 weighted images, as well as flare, empurage, and double inversion recovery, which are usually used clinically. In the upper row, you can see the actual acquisitions with the standard pulse sequences, which take about 15 minutes total, and we can nicely approximate these from just a 2-minute acquisition. One problem here is that this MR physics-based dictionary matching takes a couple of hours because it's a compute-intensive process. So we were wondering whether there is a self-supervised approach to make this also faster. So what we came up with this was just taking these 5 input images, directly using them as inputs to a CNN, and directly get T1, T2, and parameter proton density maps in an entirely black box fashion. But then we can start from these maps and directly apply our MR physics simulation to synthesize what we can get out of this network. We can then go ahead and compare what we synthesize with the input data and try to backpropagate the network weights based on this. Again, we don't need any training database. This is entirely data-driven. So basically, we use AI for optimization in this case. If we do this from scratch, this still takes 1.5 hours, but if we start from a pre-trained model, this can be done as fast as in 10 seconds. But you can see that there are some discrepancies. So we would like to address this by fine-tuning a little bit to nicely improve the data quality. In this case, this total thing takes about 15 minutes, nicely allowing us to go 5-6 times faster. So I so far talked about some MR background applications facilitated by AI, but in the remaining couple minutes, I want to talk about some of the applications which are enabled by AI. And what I want to look at is the need for gadolinium dose reduction. So GAD-based contrast agents are used in many of these pediatric brain MRIs in the US as well as across the globe. These are very helpful because this gives us more contrast and more conspicuity. You can see this on the right figure. This is after injecting this contrast agent. In the tumor case, in the middle of the field of view, we can see that this nicely gives us bright signal. And this information is important because tumors that are enhancing, which become brighter, are actually more malignant compared to those that don't. So this is quite critical information. The problem is that GAD is actually retained in the brain. So children who receive this across their lifetime, tumor patients, this keeps building up in their brain. And of course, their brains are still developing and it's quite susceptible to heavy metal exposure. So this is something we would like to avoid. And secondly, if you look at cases with chronic kidney disease, these people cannot actually get rid of gadolinium that has been injected to their bloods. So this really precludes GAD injection in these cases. And these patients have to turn to suboptimal imaging modalities such as CT. So obviously there is a need for reducing GAD dose in the clinical cases, but unfortunately there is no physics-based solution to be able to do this. So we can turn to AI and ask the question whether we can estimate full dose images starting from low dose data. And this is something we also did with Subtle Medical. So what you can do is start from a 0% dose data, which we always acquire clinically. We can then begin to inject just 20% and get a low dose acquisition, after which we do a second injection and inject the remaining 80% of the contrast to obtain a full dose data. We can then go ahead and train a deep learning model that takes only the low dose and the 0% dose and tries to predict the 100% dose data. Having done this, when we deploy this model, all that we need is the 0% and the 20% dose. We can then chuck these into our deep learning network and try to predict the full dose acquisition. And here are a couple of cases in terms of how well this works. I think in the upper row is an 18-year-old female, bottom row is a 13-year-old pediatric case. Again, the first two columns are 0% as well as 20% dose, and the rightmost column is what the AI can synthesize using these. And in the third column, you can see the actual full dose acquisition. You can see a nice correlation between the two, especially if you look at where the arrows are pointing at. We can also go back and do some sort of a automated tumor-based segmentation to be able to better compare AI-based synthesis versus the ground truth data. And we can nicely obtain DICE scores that are more than 90%. Again, nicely demonstrating that this solution can be quite viable. So with this, I'd like to conclude by thanking my collaborators and my lab, and thank you so much for the invitation. Thanks.